In this section, we're going to be going over the mean value theorem. So before we go over the mean value theorem, let's introduce Rolle's theorem. So let f of x be a function that satisfies these following three conditions. Let's say that f is continuous on a closed interval a to b, f of x is differentiable on the open interval a to b, and f of a equals f of b. So that means the y-coordinates for the endpoints are the same. Then there has to be some number in that interval such that f prime of c equals 0, meaning that there's a horizontal tangent line somewhere. So before we take a look at these examples on the bottom of the page, let's just kind of draw a quick little example right here in the middle. So these conditions, f of x is continuous, f of x is differentiable, and the endpoints have the same y value. So let's say we have, here is x equals a, here's x equals b, so those are the endpoints, and we know that their y-coordinates are the same. So that means, let's say both of their y-coordinates are right here. And now on this closed interval, so I filled in the circles on the end for the endpoints, it's continuous and differentiable. So there's no cusp here, and it's continuous. We can draw it without picking up our pencil. So maybe it might look something like, it could look something like this. No matter how you draw it, there has to be some value c, some x value c, such that f prime of c equals 0, which means horizontal tangent line. Which hopefully seems pretty obvious once we draw it out like that. That has to be the case. Okay, and then we see these other examples here on the bottom. We have, if a and b are our endpoints, we have a straight line between them. Then any point between a and b would be a horizontal tangent line. Similarly, we have right here, a to b, it kind of looks like what we drew. There would be a horizontal tangent line right here. And then for the next one, we have a horizontal tangent line here and here. And then for the last one, we have a horizontal tangent line right here. So our main use that we're going to be using with Rolle's theorem is going to be proving the mean value theorem. So here is the mean value theorem. So what we just did for Rolle's theorem is we said the endpoints had the same y value. Now the y values are going to be different. So mean value theorem says if f is a function that is continuous on the interval, differentiable on the interval, so same as before, then there has to be a number c in the interval such that f prime of c equals f of b minus f of a over b minus a, which is just the slope formula. So this means that there has to be some point c such that the slope of its tangent line has to be the same as the slope of the secant line between the endpoints. And what we can do is we could write it like this as well. That's just essentially multiplying b minus a over here to the right, or to the left. Okay, and then I just wrote down here exactly what I said before. Okay, and right here is what I said also before, but now it's just in words here. And as usual, let's see a visual here to see what this means. So this first example here on the left with this graph, we have this, the black curve is our function. We have our endpoints a and b. And now see, the y values don't have to be equal for the mean value theorem. The y values are different. We have this secant line. Let me just change the colors here. We have this secant line between the endpoints, right? So that secant line has some slope. The mean value theorem says that there has to be a point c in this interval such that the slope of the tangent line for c, or at c, has to equal the slope of the secant line between the endpoints. So we can see that it does. It looks like these lines are parallel, right? Okay, and then we have this other example here on the right. We have these two endpoints, A and B. We can see that the y values are not equal. We create a secant line between them, so there has to be at least one spot in the interval, A to B, such that there is a tangent line with the same slope as the secant line. You can see that here we actually have two of these points. We have this tangent line that's parallel to the secant line, and then we have this tangent line that's also parallel to the secant line. So there can be more than one, but there has to at least be one if it's continuous and differentiable on that interval. Okay, so let's see an example. Verify the functions satisfy the hypotheses of the mean value theorem on the given interval, then find numbers c that satisfy the conclusion of the mean value theorem. Okay, so we have f of x equals x cubed minus x on the interval 0 to 2. So we already have a picture here, but we'll come back to that in a second. So we need to verify the function satisfy the hypotheses of the mean value theorem. So f of x here, we have to verify that it's continuous and differentiable. So since f of x is a polynomial, polynomials are differentiable and continuous for all real numbers, from negative infinity to infinity. So no matter what interval we're looking at, f of x in this case will be differentiable and continuous. So we just verified that it satisfies the hypotheses of the mean value theorem. So now let's find the number c that satisfies this conclusion of the mean value theorem. Okay, so what we're trying to do is we see that we have our endpoints 0 to 2 over here on the graph. We have a secant line, the blue line, between those endpoints. We're trying to find this number c such that the slope of its tangent line is the same as the slope of the secant line between the endpoints. Okay, so let's go ahead and write down our little formula that we use. We are looking for c such that f prime of c equals f of b minus f of a. So this is just the slope formula from the previous page over b minus a. Okay, so before we do anything, what we should do is we need f prime of c, right? So what we actually have to do here is we need the derivative of the function. So we have to take the derivative, f prime of x. We get 3x squared minus 1. And now what we have to do is we have to use that for f prime of c. So instead of writing f prime of c, we can use f prime of x and just replace the x with a c. So it's going to be 3c squared minus 1 instead of 3x squared minus 1. So all this is the derivative, but instead of an x, we have a c. And then on the right-hand side, we are going to do f of b minus f of a over b minus a. So we do need to find f of b and f of a. Those are just the y values of the endpoints. So I'll just move this down so we have room. Okay, so let's find f of b. Well, right, f of a, f of b. F of a here is our 0. B is our 2. Those are just our endpoints. So f of a is f of 0. We plug it into our original function here. That's going to be 0 cubed minus 0, which is obviously 0. You don't have to show your work for that. And then f of b is f of 2. Plug it into the function. 2 cubed minus 2 is 8 minus 2, so 6. So we have f of b, we have f of a. That's going to be 6 minus 0 over b minus a is 2 minus 0. And now all we have to do is solve this for c. So it's going to be 3c squared minus 1. 6 over 2 is 3. And now we're going to add 1 to both sides. 3c squared equals 4. Divide both sides by 3. C squared equals 4/3. And now we have to take the square root of both sides. So when we take the square root, we have to remember that we get plus or minus. So plus or minus the square root of 4/3. And let's just clean this up a little bit. So that's going to be plus or minus the square root of 4, which is 2, over the square root of 3. And let's rationalize the denominator just so we remember how to rationalize the denominator. We would do that by multiplying by radical 3, numerator and denominator. So we would get plus or minus 2 radical 3 over 3. So these are the two values that we would get for C. What we have to do now is consider what interval we are in. So we are on the interval 0 to 2. So one of these answers is not correct. The answer that we have to omit is the negative one because of the interval that we're on. So we omit the negative one. So our C value is 2 radical 3 over 3. So remember that that means the slope of the tangent line at C equals 2 radical 3 over 3 equals the slope of the secant line between the endpoints. So last example here, we have y equals the ln of x on the interval 1 to 4. So first let's go ahead and verify that it satisfies the conditions for the mean value theorem. So ln of x, we have to think, is this a differentiable and continuous on the interval 1 to 4? Well, let's go ahead and write down the domain. The domain of the ln of x is 0 to infinity, not including 0, and y equals ln of x is continuous and differentiable on that domain. 1 to 4 is within that domain, so it satisfies those conditions. Let's go ahead and actually just graph this out too so we can see the graph. So y equals ln of x looks something like this, where it crosses the x-axis at 1, and then there's a vertical asymptote at x equals 0, which is the y-axis. So we're trying to figure out a point C, an x value that we're going to call C, that has the same slope as the secant line between these endpoints. So the secant line would look something like that, and we're trying to find a point somewhere within this interval that has a tangent line with the same slope. So maybe, just to have a guess here, maybe we'll say right here, because if we draw the tangent line, it would look something like this. So it looks like those slopes are the same, they are parallel. So maybe our value of C is right about here. It should be close. It looks like it anyway. The drawing could be off a little bit. It looks like it's somewhere near 2. Okay, so this kind of helps because now we can see that there's just going to be one answer, and we kind of have an idea of where this C value might be. Okay, so let's go ahead and see what we're going to need to do. We're going to need to figure out f prime of C equals f of B minus f of A over B minus A. So we're looking for that C value. Let's go ahead and evaluate f of B, f of A, which is going to be f of 1. So I'll put f of A equals f of 1, which is going to be ln of 1, which is 0. And f of B is the other endpoint, which is f of 4. And we get the ln of 4. So I think I'm just going to leave it as the ln of 4. Typically, if we have something like an exponential or an ln, you just leave it alone unless it simplifies nicely. Let's go ahead and also find the derivative. So the derivative f prime of x, the derivative of ln of x is 1 over x. So hopefully we remember how to do that. So now let's go ahead. We have everything that we need. F prime of c, instead of 1 over x, it's 1 over c, equals f of b, ln of 4, minus f of a, which is 0, over b minus a. So those are just our endpoints, b minus a. And now we can go ahead and solve this for c. So we're going to get 1 over c equals ln of 4 over 3. Technically, you could think of this as cross multiplying. We get 3 equals c times the ln of 4. Divide both sides by the ln of 4. We get 3 divided by ln of 4. So this, we're not going to approximate it, but I'm just going to write it down just so we can see that we're probably correct. If you type this in the calculator, it's about 2.16. But we're going to put the exact answer. We get c equals 3 divided by the ln of 4. And once again, that does make sense. It looks like our c value that we chose was about close to 2, and we got 2.16. So it makes sense. So the slope of the tangent line at x equals 3 over ln of 4 equals the slope of the secant line between those endpoints. Okay, so that is it for this chapter.